Hello, everyone. In this lesson, I'd like to talk about some of the important definitions and concepts in this chapter, chapter 4. Chapter 4 is titled The Application, okay? It's titled The Applications of Differentiation. In other words, is that how we're going to use derivative. So in chapter 4, we're gonna talk about these issues, okay? The first important definitions are absolute maximum and absolute minimum. And the second, well, there are two definitions right there already, and there's two other definitions, which is local maximum values and local minimum values. So let's look at the first definition. Let C be a number in the domain of D of the function f. Then f of C is the absolute maximum value of f on D if f of C is greater than or equals to f of x. For all of the x in the domain. Well, sometimes it's a specified interval, okay? Sometimes it's in a specified interval. Absolute minimum, okay, minimum value of f on D is f of C, of course, less than or equals to f of x. And in this definition, in these two definitions, we're going to talk about local a bit later, is that you can see there's no requirement about continuity nor differentiability. Okay, so in the definition of absolute max or absolute min, there's no requirement about continuity nor differentiability. However, it does have a requirement that f of C must be defined. Okay, so f of C must be defined. So to illustrate this, so let me put this on a note, right? Note, f must be defined. F must be defined, or f of C is defined. F of C is defined. Okay. So let's look at some examples. I saw some, I'm going to take this example, for example, the first one, right? F of x equals to 3 minus 2x. Okay, so this is example number 1. Example number 1. And in a series of questions, I'm also going to take this opportunity to review some of the functions. Some of the functions you are familiar, some of the functions you may not be familiar, or you just reviewing on them. So this will be a good opportunity to get familiar with these functions one more time. So if we look at this function, obviously we are given an interval for our consideration. Okay, so this is x greater than or equals to 1. This is more or less like given the domain. But this domain is not the natural domain of the function. It is assigned. It is assigned. So graphing, this is a straight line. So I'm going to just graph it. Okay. I got the software that it will graph it for me naturally, automatically. But you can just plot 2 points and graph it. Okay. But when I do this graph, you can see not only less than 1, all of the entire number lines are covered, right? But we are only interested in greater than or equals to 1. So I'm going to make some adjustment. I'm going to make some adjustment to say 0.9 all the way to 9. This is part of the picture, okay? And -8. And over here is +8, just to see what we get this picture. I leave a little bit because at 1, right, when x is equals to 1, when f is, well, at the point 1, if we plug in the numbers, obviously it is defined. It is defined. So this is 1, replace it by 1. So x will be replaced by 1, and it equals to 1. So this point, input 1, output 1, this point is on the curve. And here, of course, is a straight line. Okay, it's a straight line. I'm going to make this a dot in red. Okay, so we only consider this function for x is greater than or equals to 1. So only on this piece. All right, only on this piece, on this line. It's not, you know what, maybe I should leave some space, because otherwise it looks like it's on the y-axis, which is not true. Okay, so leave a little space. So we only consider the red dot to its right for infinity. Okay, until infinity. So the interval we are considering is really this one. Okay, the interval of our consideration is 1, positive infinity. So that's the interval in our consideration. So let's look at the absolute max, absolute min in this case. Absolute max and absolute min in this case, right? And it's obviously this point, right, is the highest point. The rest of the point is just to keep going lower and lower indefinitely. Okay, so what do we say about, I'm just making more adjustment. Okay, so what do we say about the absolute max or absolute min? Well, the absolute max is defined that f of c is greater than or equal to all of the rest of the function's value. In our case, f of 1 is the largest, right? The rest of them, obviously, they're all going to be smaller or at most the same. At most the same. In fact, the rest of them actually all smaller. They're all smaller. So f of 1, so we have an absolute minimum. We have an absolute maximum. my bad. We have an absolute maximum because f of 1, which is how high it is, this is how high it is, right? It's higher than the rest of it. So then what do we say? Okay, the absolute max is at c. C is equals to 1. C is the input. Okay, so C is the input. F of 1 is equals to 1. So here is the value, which is a maximum. And here is where the maximum is attained. Okay, so there's a location. Sorry, there should be 1 here. Okay, so we have absolute maximum at 1. How about absolute minimum? Do we have absolute minimum? Well, the line keeps going down, down, down. We cannot find a value. that is smaller than all of the other function values, right? So in this case, the absolute minimum does not exist. Does not exist. Okay. And so this is the first example. Absolute maximum exists, but absolute minimum does not. Okay. Now let's look at local maximum, local minimum, local max, local min. Once again, local max of f on D is if f of c is greater than equals to f of x, where x is near c. We talk about this neighborhood thing, right? It doesn't ask us how near, how close. Well, there's not a specific. As long as there's a little gap, how wide is the gap in the neighborhood of C? Doesn't matter, as long as we have a little neighborhood. And that kind of situation will be called a local max, local min. And local minimum, of course, is the lowest in a small neighborhood. How small, how big, we don't have a definitive number. But as long as we have a little interval that is true, then it's a local maximum or minimum. And once again, in this case, we certainly don't have continuity or differentiability requirement. Why do I mention this again? Because sometimes we are going to use the tool of these, continuity differentiability in search of local max, local min, or absolute max, absolute min. But it is important to understand, to find the local max, local min, or absolute max, absolute min, there's no such requirement about those continuity or differentiability. And the only requirement is this piece. Okay, so I'm going to bring this one over here for local max, local min, just to emphasize that small requirement. Okay. So we did the first example. So let's look at the second example. In these examples, we're going to discuss these concepts, right? We're going to discuss how we determine its local max, local min. Okay. Along the way, you know what? I'm going to bring these definitions along our side. So I put them in the bottom. Okay. And local max, local min. But this set of questions is only on absolute max. It's on absolute max, absolute min, and local max, local min. So I'm going to bring these concepts with us, okay, for our convenience. So we can refer to them whenever we need to, so we can better understand these concepts. Okay? So these are the definitions, right? And here are the space that we can do our thing, okay? F of x equals to x squared. This function on an interval between -1 to +2, okay? And let's see if we have absolute max, absolute min, or local max, local min. So we're going to use these examples to illustrate. Okay, so first we drew the picture, but we are not given the entire domain to consider this function. We are given an interval that is between -1 and +2. On the left-hand side is inclusive, on the right side is exclusive. Okay, so it's not a closed interval, it's an open interval on one side and close on the other side. So first we're gonna make some adjustment between -1. All right, so we're gonna have just between -1 and +2 to see this. If this will give us a good picture, okay? And that's not very nice. So let's do -4. Will this be better? All right. I think this is fine. This is fine. So the interval, okay, so first you look at the interval, right? -1 is included. -1 is included. So you can plug in, you're gonna have, you're gonna evaluate at -1. So when x equals to -1, x squared equals to +1. So we got a point, right? So we got this point, which is -1, 1, and that point is, I'm gonna put it on the graph. Okay, I'm gonna put it on the graph. It's a red dot, right? And on the other side, for 2.2, x equals 2 actually is not in the interval of our interest. Okay, it is not in the interval of our interest. So when we are doing that, so when we evaluate, even though, you know, this is just f of 2, we can plug in, right? But that point is not in our maximum minimum consideration, because local max, local min, absolute max, absolute max, absolute min, those points C, those number has to be in the interval of consideration. So this is what I'm trying to explain. So for that 2 squared, so what I'm going to do here, I'm evaluating this, I'm going to get a 4. And this, I'm going to plot a point 2, 4. But this point is going to be on the graph marked differently from the other point. So we're going to use a circle. We're going to use a circle to mark this point. What does that mean? It means that that point is not included in the consideration in search of max, min, or absolute max, absolute min. So let's look at our situation, right? So if by definition, if a point is not defined, right? Because f of c has to be defined. If f of c is not defined, it would not be a candidate for absolute max, nor absolute min, nor local max, nor local min. So that's what we're trying to say. All right? So let's look at absolute max, absolute min. Okay, you look at this piece of curve, right? And I'm also going to mark the interval. I'm going to mark the interval this time, okay? The interval, which is marking between -1 to +2, right? So this is going to be -1, 0, 2, 0, right? So this is going to be a line, okay? Oh, never mind. I should make it a colored, right? I should make a color of it. So make it blue, okay? Make it blue. And also, well, sorry, the blue is absorbed by the black. That's not a good idea. I'm sorry. So I'm going to use red, okay, for the moment. And I also want to put the idea of the dot and the circle, okay? 2, 0, circle, to tell the story, okay? The two red dots, the dot means the point is included in the consideration. The second dot I drew, it means the dot on x-axis, meaning the left end of the interval, which includes -1. On the right side, 2 is not included. 2 is not included. The x is not included. And these points are also. So this time the picture is completely clear. So now we can make our statements. We can make our statement. Okay. Absolute max. Absolute max. Obviously, we are, after this level, after the level of the dot, the higher dot, right? The function's value is getting higher and higher. It gets as close as possible to 4, but it never is 4. Never can be 4 because function is not defined at 2. So in this case, even though we see the highest point, but it's not attainable. It's not attainable because you can get as close as possible to 4, but never reach 4. So I hope you understand that concept. Okay, so in this case, we say there's no absolute max. You can see that because the interval is open on the right side, there's no absolute max. But we have absolute min. We have absolute min. Obviously, we do. We have a lowest point, which is 0, 0, right? We have an absolute minimum at a 0, at c equals 0, right? The lowest point is right here. And c can be 0 because 0 is covered, 0 is in the interval of consideration. So the lowest point is right there. The lowest point is right there. We have absolute min, the absolute minimal value is f of 0 equals to 0. Okay? So absolute max, absolute min. And now what else? We have considered absolute max and we have considered absolute min. We know there's no absolute max. And we have local max, local min. We have local max, local min. Well, yes, we do. We actually have a local maximum because you can see in the neighborhood of -1, in the neighborhood of -1, there is a little neighborhood, right? To the left of it, there's nothing there because function is not defined there. But to the right of it, we have a little neighborhood, right? It's just a little neighborhood. In this little neighborhood, this dot is the highest, So this dot, okay? So this dot is the highest in a little neighborhood, in this little neighborhood. Therefore, we have a local max at what? At 1. Sorry, at a -1, sorry. At a -1. Okay? And its value, we already calculated the value. The local maximum is f of -1. But do we have a local minimum? Do we have a local minimum? Do we have one? If you say no, and I have to disagree, because we do have a local minimum, which is 0, 0, 0. If it is absolute minimum, it must be a local minimum. Okay, let me say this again. If it is an absolute minimum, it must be a local minimum. And it's the same is true for absolute maximum. If we have an absolute maximum, then it must be a local maximum. Then you say, how about we go the other way around? Okay, so let's discuss that. Let's discuss that. So we do have a local minimum. The local minimum happened to be at the same place we have absolute minimum. Okay? So I wish you guys to think about it. Maybe you want to pause a little bit to think about this question. Okay, to think about this question. All right, I'm going to type the question. So you think about these concepts. Okay, questions. Is an absolute maximum a local maximum? Is an absolute max a local max? Is an absolute minimum a local minimum? Okay. Now, is a local max an absolute maximum? Okay. Is a local minimum an absolute minimum? Think about these 4 questions. All right. So what do you think? So after you pause a little bit, then let's go back to these questions. Okay, just from the meaning of these concepts, and the examples we just did. Okay, the examples we just did. And we're going to see some more examples, but we want to have some sense of the logical relationship between absolute max and the local max, right? Now, is an absolute max a local max? The answer should be what? The answer is yes. Is an absolute minimum a local minimum? The answer would be yes, right? Because if you have if you are absolute maximum on the entire interval or in the entire domain, of course, it is also local, right? Absolute max in the entire interval or in an entire domain is the max, is the absolute max. And certainly in any small neighborhood, it is also a local maximum. However, is it true a local maximum and absolute maximum? Is an absolute local maximum, is a local maximum and absolute maximum? Not necessarily, not always true, right? Not always true. In our previous example, you can see at -1, we have a local maximum. We have a local maximum, but is it an absolute maximum? We have other values which are bigger than that one. right? So that is not always true or not necessarily true. Not necessarily true. Okay? Why we say that instead of saying false? Because sometimes it may be true. Okay? Sometimes it may be true. And it's the same for local minimum. So it is a local minimum and absolute minimum. It's a local minimum and absolute minimum. Sometimes it's true, sometimes it's not true, right? In our case, we have this one is a local minimum as well, right? And it is also absolute minimum, okay? But what's a logical relationship, right? So we got yes, true. Having these concept logically figure out this way helps us. And the other thoughts of to find absolute maximum or absolute minimum would be that maybe we can find all the local max. And from the local max, we find the absolute max. That's another idea. And the same could be for local min. Find all the local min, and from among all the local min, maybe we can find an absolute min. So that's another idea. Okay? So let's look at some other examples. And we are also going to test drive these concepts and ideas. Okay. Now, so let's look at example number 3. And example 3 and example 4, we're going to work on them like next to each other. And f of x equals to 1 over x is a pretty familiar function, isn't it? But we are only considering this function from x greater than or equals to 1. So now let's draw this picture. Okay, trust that you know how to draw this picture. Just plot some points, right? So this picture gave us from negative infinity to positive infinity other than 0 because x is not defined as 0. But we only want to consider x greater than equals to 1. Therefore, we're just going to be just look at these functions, just to look at the piece on the right side of the y-axis. Okay, so here we go. We just have this little piece. We just have this little piece. And when x equals to 1 is in the interval. Okay, so when x is equals to 1, f of 1 is equals to 1 over 1 equals to 1. All right. So I'm going to plot this point. We got point input 1, output 1. Input 1, output 1. So we're going to have a dot, right? So you learn to use a dot and circle will help us to figure out what is, the point of interest, right? What is the point that here I use a black dot. Okay, I think that's okay. I don't need to take time to find it. And from positive 1 all the way to infinity, And obviously we have an absolute maximum. We have an absolute maximum. Okay, we got an absolute maximum at 1. But do we have, and of course, f of 1 equals to 1. Right? But we have absolute minimum. You can see the curve will get lower and lower and lower, right? We can even use the limit because the limit of this function and as x approaching infinity, right? The limit of f of x 1 over x as x approaching positive infinity is 0, right? So it gets infinitely close to 0, right? Because our interval is from 1 to positive 1 to infinity, including 1, but it will never touch 1. It will never touch 0. Even though 0, we can get as close as 0, but 0 is not the absolute minimum because that x, whether, where is it, we will never be able to locate it, okay? You don't have to introduce limit in this sense, but you just know it's not attainable. It's not attainable. So there's no absolute minimum. Oh, sorry. No absolute minimum. Okay, no absolute minimum. Now, do we have local max, local min? Well, absolute max is local max. And we don't have local minimum either. Okay, so we also have a local max, right? X maximum, which is also at 1, right? But we don't have no local minimum. All right? So we get familiar with these pictures. All right. So let's look at the next one. The next one would be a little bit more interesting because this picture it's the same picture, it's the same graph, almost the same graph. But we have two circles. Okay, so I'm gonna kind of stealing from this picture. Okay, so I'm making some adjustment. This is from 1 to 3, but we know that this time 1 is not included. So that I need to change 1 to a circle. Okay, and the 3, right? The function is not defined at 1, not defined as 3. So for f of 1, we know f of 1 is equals to 1. F of 3 equals to 1/3. But these 2 points, they are not in the interval of consideration. In other words, we're looking for the number where we get the max or min, C, but C is nowhere to be found. We can only get infinitely close to the lowest or the highest. Okay, so I'm going to plot another point, which is 3, 1 over 3, and this time is a circle again. And the interval of our consideration, hold on a second. And this one need to be a circle too, right? Sorry, we have 2 circles. And the interval of consideration. So I'm going to put the interval of consideration, okay? 1, 0, 3, 0. And that's a line, and thickness, I'm going to make it red, right? I'm also going to mark the circles, 1, 0, circle, right? And 3, 0, circle. 2 circles, right? So these circles. So you can see we're trying to find the max, we're trying to find the min, right? So This piece, obviously, we can get it as close high as possible, but never get to be there. And so in this case, we don't have absolute max, and we don't have a local max, and we do not have absolute min, and we have no local min either. So it's an open interval. That's what happens when we have an open interval oftentimes. Okay. Not always, no, not always though. Okay. Oftentimes, I said. So what do we say about absolute max, absolute min? No absolute max. Okay. And no absolute minimum. And we also have no local max, right? We don't have a little neighborhood that's the highest nor lowest, okay? And no local, whoops, no local minimum. It just does not exist. None of these max, min, local, or absolute exist. And do this happen? Yes, it does. Okay. Wait a second. Yeah, we're good. So I'm gonna I don't need this picture. I don't know how you get there. All right. Sine function. Okay. So you have two sine functions examples here, three sine functions right there, right? I'm gonna use these three functions in a comparative study. And we want to see the sine function between 0 to pi over 2. 0 is included and pi over 2 is not. And hopefully by this time, you guys have done some review of sine function, right? And this is, your calculator or anything, we just make a sine curve, but we're really interested in the interval between 0 to pi over 2. So I'm going to just make some adjustments, okay? Pi over 2, and this is going to be from -1 to +1. Sine is between +1 and -1. Wait a second. I don't want to lose that shape, actually. So I'm going to make this, oh, never mind. My bad. Okay, I don't want to lose the shape. So I'm going to mark the points, okay? Even though most of it we don't need, right? I'm going to mark the interval first, okay? We're going to mark the interval. The interval is going to have 0, 0 from 0. 0 is included, right? I'm going to use a black dot because sometimes the dots kind of get to us, okay? And the other one is pi over 2, which is not included, not included. That got to be a circle. Okay, that got to be a circle. So the interval is being marked. Okay. Is that color okay? It looks fine. And I'm going to mark the interval, by the way. Okay, so that will make it easier for us to see. Okay, so 0, 0, pi over 2, pi over 2, comma, 0. And we're going to use red interval, make it a medium. So this time we see better. The left is a dot, which the endpoint is included, the other one is not. And let's see what's on the curve, right? Let's see what's on the curve. On the curve, we already have a 0, 0. That was the point. And for pi over 2, where the function is not defined in this question, right? So it's going to be a circle. It's going to be a circle Let me use red. Let me use red. There. Okay. So obviously we have an absolute minimum and local minimum, but we don't have absolute max nor absolute min. Okay, so by this time, I hope that you got it. If you don't, let me know. Okay, we have absolute minimum and local minimum at 0. Okay, and the absolute and the value of it is, well, sign of 0 is 0. And we got no absolute maximum, nor local maximum, nor local maximum. All set. Okay, but we're studying this time function from two for 3 examples. So that's how we can clarify our, idea about the concept, right? So I'm going to take this same picture. I'm going to I'm just going to make some changes, right? So this should be pretty, I hope it's fast. So this time, the 0 part is the dot. Pi over 2 is changing from circle to dot, something like that. And of course, the other point need to be changed. Pi over 2, 1. That needs to be a dot. Now what do we say? This time, right? Last time we don't have, this time we have absolute max. Absolute max. Sorry, I put it in here. Absolute max at what? At a pi over 2. At pi over 2. It's all because pi over 2 is now included, right? And the f of pi over 2 is equals to 1. So that's a maximum value. And of course, it's also going to be a local max at pi over 2 as well, right? So all those questions are answered. Now, how about minimum? This time, there's no absolute minimum nor local min. They're not necessarily logically related. It's just in this case, we don't have a local max, a local min, and absolute min. Okay. Sometimes we have a local min, but we don't have absolute min. Okay, we will see those examples in the future. Okay. Okay, the third case is a completely closed interval. So you can see in the previous 2 examples, right? In the previous 2 examples, the interval is half open. The half open. And then you start thinking, if we have opening, if you have any open on the interval, either left or right, and then we may not have the one of the local max or absolute max and so on and so forth. So let's look at number 7. And number 7 is an entirely open, closed interval. Okay, so I'm going to redraw the picture. Okay, sine x. We draw the picture. We're only going to look at from negative pi over 2 to pi over 2. And because these 2 points are included, so it's a closed interval. So let me just making an adjustment. Just making an adjustment. One, positive 1. There we go. Just from negative pi over 2 to pi over 2. So I'm going to mark those points, right? So negative pi over 2, and that should be a dot. That should be a dot, okay? And another one, positive pi over 2, that should also be a dot. No circles, so that is the interval. And the sign of, pi over 2, -1, and that should be a dot as well. That should be a dot as well. And the positive pi over 2, right? So that function is also going to be a dot. No circles. So what happened now? Let me mark the interval one more time. So here, there's a 0, pi over 2, comma 0. Okay, we're not going to use a red color to mark the interval. So you can see the interval is closed, and we have absolute max and absolute min. And they are, of course, in turn, local max and local min. We have everything. We have everything. So let's write it down. What is our conclusion? And then we're going to do the three question comparison. Okay, 3-question comparison. All right. So absolute max at positive pi over 2, which is the highest point, which is attainable. Okay, f of pi over 2, f of pi over 2 is equal to 1. Absolute minimum at negative pi over 2, which is f of negative pi over 2 equals to a -1, right? We know those properties. And all of these, we have a local max at here at the same place as absolute max. And we also have local min at negative pi over 2. Same thing. Okay. Now we come to an interesting observation. So because we're going to do the comparison of these 3 examples, right? Functions are the same. The first 2 examples, both are half open. Then we have sometimes we have one, we don't have the other. But for closed, we have both. Isn't that interesting? Well, as a matter of fact, there's then this is the time we're going to introduce extreme value theorem. Extreme value theorem. What is extreme value theorem? Okay, extreme value. So what are the extreme values? In our consideration, extreme values are either max or min, whether it's local max, local min, absolute max, absolute min. Those are called extreme values. The extreme value theorem has one condition and one condition only. Okay, so here it comes. If f is continuous on a closed interval, A smaller, B is larger. Okay, there's only one condition. Then, okay, here it comes. F attains an absolute maximum value f of c, or f of c, okay, and an absolute minimum value f of d, f of d. C and D are the place where the absolute max and absolute min, okay? At some numbers in some numbers. So this is just to say C comma D, okay? And some numbers C and D in the interval we just talked about. So this theorem to tell us if you get a closed interval and the function is continuous, you always have absolute max, absolute min, always. And of course, we're going to talk about how to find them, right? How to find them. But in this lesson, we're just going to, this is the opportunity we review some simple functions. Let's continue. Let's continue. Number eight. Number eight. Number eight. Number eight, we're given a closed interval. So what can we draw? What can we tell from this? Well, cosine function is continuous everywhere. Certainly, it is continuous on the closed interval given, right? So this is the moment we can apply extreme value theorem on this function. And how do we apply it? This is what we can say. We can say f of x, right? Okay. This is not an if. We're certain this f of x is continuous on what? Well, on this interval from negative 3 pi over 2 to positive 3 pi over 2. It's a closed interval, okay? Then we can apply, because we can say because f is continuous on the closed interval. Sometimes you can remove, right? You can remove this. You can say this is much easier, it's much simpler. And the closed interval, those words are being replaced by actual the way of writing, because you write a closed interval. So you can say f is continuous on this closed interval. The reader say, oh, it's a closed interval. You're good, you're good. So either you write it that way, like this sentence, or you write it this way, which is fine. Okay, same thing, okay? And then we are certain there'll be absolute max, absolute min, and let's see what they are. Let's see what they are. And we are going to use a graph because this is the instruction for this part of the questions, okay? For all of these questions from your homework. So what do we have? And we're going to, this is the negative. So we're gonna have -5, +5, right? This is about right. Okay, we can remove that. So we're going to figure out the interval. We're going to figure out the interval, right? The interval, we're going to draw that interval. Okay, it's a closed interval. Closed interval, so it's a negative 3 pi over 2. Oops, 2 comma 0. This should be a dot. Okay. And the other one is going to be a dot. And the interval, which is in between, three pi over 2 comma 0. And that's the interval we are considering. It's a closed interval. It's a closed interval. Okay. So now let's look for the local max, local min. Oh, and the absolute max, absolute min. Okay. Obviously, we have a couple of bumps, right, with the highest point. Well, obviously, this is going to be absolute max. It's attainable. It's inside the interval. So the absolute max is at what? Is at 0. Okay. And f of 0, we know cosine 0 is equals to 1. Cosine 0, okay, f of 0 is equals to 1. So that's absolute max. How about absolute minimum, min? We got 2. We got 2, right? We got 2 absolute min. Okay, we got 2 absolute min. And where are they? Where are they? Well, in fact, this point is negative pi, and the other one is a positive pi. Okay, absolute min are at negative pi and the positive pi. And positive pi. As we know, we talk about cosine is even function, right? Of course it is. So they have the same value. F of pi is equal to f of negative pi, right? And that equals to negative 1. So absolute min. So we got all the absolute max, absolute min. How about local max, local min? Well, local max, the absolute max are local max. Okay, absolute max at 0 for sure. We have more. Do we have more absolute max? Do we have more local max? Yes, we have 2 more. We have 2 more. Where are they? Where are they? There's one here. There's one here. These are local max. These are local max. Okay. You see, they are not absolute max nor absolute min, but they are local max. So the local max at what point? At a negative 3 pi over 2 and 3 pi over 2. Okay, so we have 2 other local max. Okay, so local max at 2 more points. One is a negative 3 pi over 2. And positive 3 pi over 2. And what are the local max value? Because there's a little neighborhood is the max, right? In the neighborhood is a max. So f of because the cosine is even function, so cosine of negative 3 pi over 2 is the same as cosine of 3 pi over 2 positive. Same value, right? It's even function. So that's the cosine 3 pi over 2. Cosine 3 pi over 2 is equal to 0. Now look at that. Look at that. We have learned to identify, okay, absolute max, absolute min. Sometimes we have more than one place that attains absolute max, absolute min. And we also have local max, which are neither are absolute max, but they're local max. Now, let's look at the question. Do we have local minimum? Do we have local minimum? Yes, the absolute minimum are local minimum. So local minimum in this case are at 2 points, okay? So now we learn how to identify these values, right? Okay. Let's look at example number 9. Now we are equipped with 4 definitions of absolute max, absolute min, and local max, local min, and also extreme value theorem. So let's look at example number 9. This interval is half open, half closed. Can we apply extreme value theorem? The answer is no. Extreme value theorem does not apply here. That means that the conclusion that extreme value stated is may or may not be true. I say may or may not be true, right? It's not guaranteed. There's no guarantee. If the condition of extreme value theorem are satisfied, which is continuous on closed interval, then we surely have absolute max and absolute min. But if it is not continuous on, or if it's continuous on a half closed interval, then we're not sure, we're not certain. Okay, so extreme value theorem does not apply here. And what can we do? Okay, so let's gain some understanding of the, get familiar with, with this function, right? Ln x, we've drawn this picture, we've studied this picture, reviewed. So let's look at this curve. Okay. The domain of ln x is x greater than 0, right? And we certainly have an interval inside the domain. So zero side, right? 0 side is a circle. It's a circle. Okay, and the other side, which is x equals to 2 ln 2, and that should be a dot. That is a dot. And the interval in between, right? And we got the interval in between. The interval in between, right? So let me bring that interval for you. So we got here, make it red. That interval is this half. Oops, what did I do? I'm sorry. I did something wrong. 0. Okay. All right. And at 2, 0 should be a dot. 2, 0 is a dot. There we go. So this interval is half open or half closed. You can say that too. Okay, if I adjust my picture a little bit, right, I can make it a -3, -4, and maybe just Still the 2, which is fine. Okay, we made a little adjustment here. Maybe a little bit too much. Okay, so it's -2 then. Okay. In this direction, it goes to negative infinity, right? Obviously, we do not have absolute min. And we do not have a local min because the curve is increasing, right? Keep going up. But we do have absolute max, okay? So absolute max on the interval is at x equals to 2. And what is the, you can, yeah, at x equals 2 and f of 2, the absolute max value is ln 2. Done, right? And of course, this is also local max. This is also local max, right? Absolute max is local max. We have local min, we just talked about. We have no local min nor absolute min. No absolute minimum. You can see if the condition of the extreme value theorem, right, does not apply, is not satisfied, we don't know what's going to happen. No certain conclusion. No certain conclusion. That's what we can say. Okay, for the next 3 functions, okay, before we touch that two, before we touch those 2 piecewise functions, these 3 functions that we were not given an interval. It's just their natural domain. Let's see what can we tell. This function should be pretty familiar to us, is that V-shaped function for absolute value of x, right? So I'm drawing this picture here. Obviously, we have an absolute minimum at what? At 0. Does extreme value theorem apply here? The answer is no, because the interval of the domain for this function is from negative infinity to positive infinity. Okay, we're not given any specific interval, so its domain is the interval of consideration. So from negative infinity to positive infinity, this is open interval. We don't know, but we have absolute min at 0 and f of 0 is 0. Right, so the absolute minimum value is 0. We got that. But do we have absolute max? No. We don't have absolute max. Okay. Do we have local min? Local min is the absolute min. Okay, same thing in this case. But do we have a local minimum? Oh, sorry, this is local max. Sorry, local. Oh, I'm sorry, local min. What am I saying? Do we have local min? Do we have local max? No. No local max. No local max. All right. Okay. 11. Okay, so for 10, we cannot apply extreme value theorem. Okay, so extreme value theorem does not apply here on number 10. Does not apply. Okay, so number 11. Number 11. So we're going to draw the picture and look at this domain. We're not given any specific interval. So what is the domain? So we need to determine the domain. The domain will have to guarantee the root function is meaningful, right? And the domain for root x is x greater than or equal to 0. So x greater than or equal to 0. So this is an open interval. It's half closed, half closed. So on this interval, right, on this interval, we're going to mark it. Okay, so we're going to mark, this is 0, 0. It's going to be a dot, right? And so 0, 0. Never mind I'm just using the software for our purpose, okay? And so this is going to be that. So on the right it goes forever. I'm going to need to have a set of view. Okay, this view is just a little bit too much. Okay. Maybe even that's even too much. -4 and 1.2. Just make that. Okay. So that's the function. And on the left end, we have, well, x equals 0. The highest point is 1, right? So 1, 0, 1 is the highest point. It should be a dot, not a circle. So obviously we have absolute what? Absolute max at 0, which is f of 0, right? F of 0 is f of 0 equals to 1. So that's the absolute max, which turn out to be also local max. Do we have absolute min? Do we have absolute minimum? Do we have absolute min? Okay, the answer is no. No absolute min. Do we have a local max? Local max. Yes, local max at the same place, the same maximum value. Do we have local minimum? No local minimum. Okay. No absolute min does not guarantee we have a local min or not. Okay, because we will see that in the future. So these two are not necessarily, related in that way. Okay, let me repeat. If we don't have absolute min, sometimes we may have a local min. All right. Number 12. Number 12. This is the function that I want you guys to be so familiar with. Okay. And this is how the curve looks like. The curve will never touch x-axis. Okay. The curve will never touch the x-axis. And the entire curve is above x-axis. Okay, it's just like 2 to the power x or 3 to the power x, right? So the domain, of course, domain is all real numbers. If domain is all real numbers, then that means, I may not have to forget to save. Okay, domain is all real numbers. Does extreme value theorem apply? No. Extreme value theorem does not apply here. Do we have absolute max, absolute min? No, we have no absolute max nor absolute min. No local max nor local min. Yes. You can see we have a couple examples here, right? One extreme value theorem does not apply. Sometimes we don't have anything. We have no extreme values. No extreme values. Okay. So last two. Okay, I'm gonna see if the software will graph it for us. Okay. Otherwise, I have to mobilize using some other means. All right, it looks like it does it for us. Okay, thank God. All right, but we need to make some changes. For example, I need to add some dots. Okay, so let's see what the picture, the graph, the software has generated for us, right? Between -1 to 0, we have x squared, right? So this is a closed interval. This is a closed interval. And now we got, I don't need to make an adjustment to, yeah, it's pretty good. It's pretty good. And next, I'm going to mark some dots and stuff, right? -1 is going to be a dot. So -1 is a dot. Okay. 0. A 0 is tricky. When x equals 0, the function, we use the first rule, which is x squared. So that's 0, 0. So 0, 0 is a dot. 0, 0 is a dot. At 0 on second rule, this second rule is not used on 0. So on this point, it should be a circle. Is it going to be a circle? So I'm going to draw a circle, right? So for 0, 2, that's going to be a circle. Circle. There we go. And last one, right? On 1 less than or equal to 1. So that should be a dot. That should be a dot. So 1, 0 is a dot. Okay? And the function is defined actually on the closed interval between -1 and +1, right? The function is defined on this closed interval between -1 to +1. Now question, can we apply extreme value theorem here? Can we apply extreme value theorem? Well, to apply extreme value theorem, we only have one condition and one condition only, which is this function has to be continuous on the closed interval. Is the function continuous on the closed interval? Obviously, on this end, it's right continuous, left continuous, but it is not continuous at one point. So how are we going to make the case? How are we going to make the case? Right? Using the definition of continuity. Okay, so review your definition of continuity. So why the function is not continuous? If a function is not continuous on a specific interval, then if it is not continuous at one point, then it is not continuous on the interval. Okay, so that's the logic. So first we have identified this function is not continuous at 0. F of x okay, is not continuous. So first we need to explain it is not continuous at 0. And 0 certainly is on the interval, right? So why? Certainly it's defined, right? So what rule are we going to use? So this is what I suggest, okay? You may pause and do your own and come back, okay? But I'm going to get it done, okay? Otherwise it's going to be too long. And you may pause and come back, okay? Well, x is approaching 0 from larger than 0, f of x, what does that equal to? We're going to have to use the rule of the function. We're going to use the second rule, right? The second rule is a direct substitution. It's going to be 2 minus 3 times 0, right? So that's going to be a 2. But what does f of 1 equal to? F of 1 is, what is f of 1? F of 1, we're going to use the first definition, right? I'm sorry. F of 0, my bad. F of 0, right? We're looking at 0, my bad. F of 0, we're going to use the first rule. That's going to be 0. So what do we get? We get the limit of the function from larger than 0 is not equal to the function's value at 0, right? So we declare f is not continuous at 0 because these are the reasons, okay? You can also say since, right? Since all of these reasons, then you can say f of x is not continuous at 0. Thus, f of x is not continuous on the entire interval. Because if it's continuous on the interval, it should be continuous at every point on the interval. Left continuous, right continuous, all satisfied. So if there's a one point the function is not continuous at, then the function is not continuous on that interval, okay? That was the basic definition in your index card and in the textbook. Thus, extreme value theorem does not apply. That means there's no guarantee of absolute max, absolute min then. But we can still look for them. So let's see what we got. Okay, we got some dots, we got circle, we got dots. So let's see. I'm gonna put the dots in place. Okay, I'm gonna put the dots in place. And another point is a 1, -1. Okay, so these dots. So we got all these dots and circles in place. Okay. Do we have an absolute max? Do we have an absolute max? The maximum value that's going to be above everything? The answer is no. This is the highest dot before we see the other side. And this side, this is higher. But we can get infinitely close to the circle on the very top, but we'll never attain it. We'll never attain it because that piece of function is not defined as 0. So in this case, we have no absolute max. Okay, no absolute max. Let's see, do we have absolute min? Do we have absolute minimum? Yes, we do. We have absolute minimum at 1. Okay, we have absolute minimum at 1 from this picture. Okay, which is -1. So f of 1 equals to -1. We found it. Okay, so we have no absolute max, but we have an absolute min. So let's look at local max. Do we have local max? Yes, we do. We have a local max at -1. So even though we don't have absolute max, we have local max. Local max at -1, which is f of -1 equals to +1, right? Do we have local min? Do we have local min? Yes, in this, wait a second. Wait a second. Okay. Do we have local min? Obviously, this is 0, 0 look like a local min. Of course, the absolute min is a local min. Okay, so we have local min for sure at 1. We have local min for sure at 1. But do we have another local min? Do we have another local min? We say at 0. Well, the problem is the neighborhood. We mean the neighborhood a little bit to the left and a little bit to the right. A little bit to the left is the lowest point, but a little bit to the right is no longer. Oh, wait, is it? Is it the minimum? Is it a minimum? Is it smaller in that neighborhood? Is this the smallest in that neighborhood? A little bit to the left, a little bit to the right. This neighborhood, okay? So let's take a close look. And I want you guys to bring out your little index card. Okay, so in this neighborhood, right? Is in this neighborhood, this dot the lowest one? That's the question we are asking. I think so. I think so. So we not only have a local min where the absolute min is, we also have another local min. So local min at 0. Okay. And of course, f of 0 equals to 0. Interesting, isn't it? This question, I think, is definitively very interesting. It is very interesting. Okay, last but not least. Oh, wow, this lesson is a bit too long. But you guys can, you don't have to watch it in one sitting, right? Come back to it. All right. This piece, so let's look at the graph. I think by this time, you may like to pause and do it on your own, from drawing pictures and everything else. All right. I'm just going to go forward, and if you guys need to pause, you pause, okay, and work on your own. Obviously, we have a closed on the left hand or closed on the other side, and one is a point of interest, and obviously there's a discontinuity there. So this question, so let me try to get it done quickly. So from 0, right? from 0 to 3, right? This is the interval. This is the interval, right? And it's closed on both sides, okay? So 0, 0 is a dot, and 3 comma 0 is a dot. And so we got dots at the end of the point, right? So these are dots. So 0 comma 1, that's a dot. 3 of 3 comma negative 2 is also a dot, right? So we got all these dots. But how about here? The 1 is defined on the function on the right. Okay, so let's see where we're going to put the dot. We're going to put the circle. So at a 1, if we put in 1 here, it's going to be 2, there's a dot. But at 1 less than 1 is going to be a 3, is a circle. There we go. Oh, obviously, it's not continuous. So how do we say it? You can say because the limit, right? We're gonna bring up the definition of x approaching which number? Approaching 1 from smaller, right? That function's limit from left of 1 is a direct substitution, right? Is going to be 2 times, right? We're going to use the top piece, right? So 2x plus 1. Oops, sorry. 2 plus 1 in parentheses. And so that limit is a 3, right? And what does f of 1 equal to? F of 1 is equals to 2, right? Is equals to 2. I.e., the limit from left of f is not equal to the function's value at 1, therefore, it's not continuous, right? So we can say f is not continuous. It's not continuous at what? At 1. If it's not continuous at 1, f of x is not continuous on the interval. On the interval 0, 3, right? So extreme value theorem does not apply. Does not apply. So does not apply, what does it mean? There's no guarantee of absolute max, absolute min. So let's take a look, right? It doesn't guarantee, doesn't mean we don't have them, okay? But obviously we don't have absolute max, okay? No absolute max, okay? So typically to find absolute max, you just draw a line. You just, can I get, where is the highest, right? And here we have a very high point, but we cannot get there. We just cannot get there, right? No absolute max. But we have absolute min. Absolute min. What is it? Absolute min at 3. Absolute min absolute min at 3. F of 3 is -2. So we got absolute min. Then we have a local min, right? We have local min. All right. We taken care of absolute max, absolute min. Do we have local max? Do we have a local max? Well, this piece may be a candidate for local max, but look at that little neighborhood. Look at that little neighborhood. On this side is a max, but on the other side it's not. Therefore, this is not a local max. Okay, this is not a local max. Let me say it again. You have to look at the neighborhood. The neighborhood has a left, has a right. Okay, since left and right are both included, well, on one side is the local max, on the other side is not, therefore it is not. All right, so we don't have that local max, but do we have a local min? Okay, yes, we do have a local min. We already have one. The absolute min is a local min, but we have another local min. But in this case, you say, all right, how look at this neighborhood. Well, the neighborhood does not have the other side. Those are there's no neighbor on the other side. So when you look at that neighborhood, yes, we only have half, but in that half is a minimum. So that's a local minimum. You see the difference between these two we just talked about? Okay. So we have a local min at what? Not only at 3 and at 0. We have two local min. One is also the absolute min, and the other one is the local min at 0. Okay, so at 3 is f of 3 equals to -2, right? But f of 0 is a +1. I have two local min. And we have no absolute max nor local max. So that concluded our discussion. So these discussions are intended for us to understand these concepts well for these simple functions. And all these questions are from your homework. So hopefully this will be good for your studying. But make sure when you study, try not to look at the answers before you try it. Okay? Thank you for watching.